So welcome to video 3 in our course ST4 on linear models. So we know that we have correlation coefficients and we can transform these into other informative values going from a correlation coefficient R into maybe a t-stat or indeed a Cohen's d effect size measure. So this applies where we have a large sample size. So if we have a large sample size, we can notice that the variance associated with the correlation coefficient tends to be quite small. The exact value of that size depends. There's no strict threshold for the n to be large, but at least n of 20 or 30 would be informative. So to transform our values into t-stat, there's a particular formula that we can use, and this assumes that we have n minus 2 degrees of freedom for our corresponding t distribution. And that is a function of this, the inverse of the standard deviation multiplied by the fraction of variation that's not explained scaled by the correlation coefficient. So for example, if we have R squared equal to 0.5, with 12 samples, we get a t-value of about 3.2, which would have a low percentile on the distribution. Similarly, if we have our square root of about the same value for n equals 5 values, we find our t-value now is lower at 1.7, which is quite a less extreme value in our percentile distribution. If we relate these, then we plot the R values versus T values, and what we can see is that as we increase our T value for our given R squared value, we note that as a very sigmoidal distribution that if we use a p-value threshold here determined by this line for T of around approximating 2 for n equals 10 samples, t equals 2 and 3, 1. We can see there our kind of threshold for correlation coefficient might be around 4.1. If we have a larger sample size of n equals 50, a t-value threshold for a percentile of 5% is lower at 2.1, and our correlation coefficient threshold is lower as well, about 0.1 or 0.29, which is about here. And R equals 0.63 is around here. So you can see that our sample size has an impact on the correlation coefficient, the extent to which it has an associated p-value. And we know, of course, that our R value denotes the biological correlation that's present, and that's more informative than the p-value that we observe, which depends on our model as well. So we can look further at this model and look at this transformation in terms of the slope b that we have. So we can compute the standard error of slope b using a similar setup, but slightly different. So we're taking on board the value of b as well. So we're looking at this formula where we have y is equal to b by x plus a, the intercept. So that's the slope b that we're looking at. So we can get 95% confidence intervals using this standard error here, multiplied by the value t for n minus 2 degrees of freedom. And that is this our confidence interval. So that's just something that we'll do with our code later. If you look at Cohen's d, technically this is ds. There are different Cohen's d values depending on what you're different Cohen's d stats depending on what you're looking at. We have to consider the sample sizes. This is the sample size for population 1. This is the sample size for the second population. And if we're dealing with the same setup where we have y is equal to bx plus a, we can get these 95% confidence intervals using a similar formula, which we can write with our code as well for D. So if we look at what this would be transformed into practice, what we see on top here is for this distribution, are the R coefficient value is 0, or might be 1.17. If that estimate is 0.17, the t-value is 1.17, the rho value will be 1.4, and the t-value for that rho value will be 0.97. In the same way, for our estimate of R, the correlation coefficient is 0.22, our t-value will be 1.5, our rho value will be about the same. And again, if we go up to a correlation coefficient of 0.3, our t-value is higher, 2.2, You can see that there. We increase it further to a correlation coefficient of 0.447. Our t-value increases further to 0.8. Our t-value is much higher. And then to 0.9, our t-value is much higher again. So that gives you a sense of the extent to which these effect sizes are correlated with each other. You can see that the kind of noise in each distribution is different each time. And to remind you here that our information about these effect sizes from R squared, rho, and T, and D as well can be informative, and that tells us about the biological effect that if we persist in a p-value based interpretation of our effects, we really are losing the biological understanding of what we're looking at. So please see video 4 next on linear regression.